Okay. Any other? Yes. No. Okay. Our courses will be actually, we will continue having it on Saturdays. We were supposed to have it last Saturday also, but I mean, due to the passing of Cem Tezer'in vefatından dolayı cumartesi yapamadık dersi. O yüzden o dersi telafi etmek için bugün. Yani şimdi cumartesi olmakla ilgili sıkıntı, her cumartesi yapamayabiliriz. Cumartesi yapamadığımız zamanlarda o zaman çarşamba ya da cuma olacak ekstradan. Yani, gelenler bir sabitleştikten sonra, artma eksilmeler bittikten sonra yeniden bir oturur konuşuruz hangi saat yapalım diye. Yani uygun bir saat bulabilirsek hafta içi değiştiririz. Değiştiremezsek cumartesi devam edeceğiz. Şimdilik geliyor gibiyiz. Yani bir başka toplantımın çıkma ihtimali var ama bugüne kadar çıkmadıysa muhtemelen çıkmayacak. Bu cumartesi var. Okay, so let's go back to our discussion. Any questions on our derivation of the propagator? In fact, this is what we will, I mean, this is the, for a real free real scalar particle. So this is the case. This will be the probability for the particle to go from the space-time point x0 to the space-time point x1 if the theory was completely free. Now, if there are interactions, of course, we will be the full expression, including the effects of the interactions, is given by this expression that we obtained before. Now, in order to calculate that expression, we also need to discuss how to calculate the time-ordered products of more than two operators. You see here, we already have two operators and the derivation is quite involved. I mean, if you try to do this derivation or a similar derivation for 3, 4, 5, 6 fields, no, that won't be practical. But let's go over what we had done in this derivation. You see, we said that, okay, there is the time-ordered product. There was one simplification over here. If we had the annihilation operator on the right and the creation operator on the left, nothing contributed anyway. They didn't contribute. And then we took these terms. We had the annihilation operator on the left, the creation on the right. But using the commutation relations, we just exchanged their places. By replacing them with the commutator, we actually exchange their places. There is the additional term of phi dagger k2 plus times phi of k1 over here as an additional term, but this doesn't contribute because of the properties of the empty state. So basically, when we started with the time-ordered product, some terms in that product already appeared with annihilation operators on the right, creation operators on the left. Some terms appeared not in that order, but in that case, we just used the commutation relation to put them in that order. And all those terms cancelled in the derivation. Now, such terms such products are called what we call the normal product. So you see, we have already discussed the time-ordered product. It uses the time property of our operators. The operator that has the earlier time acts first, and then the operators at later times. What normal product does, there are various notations. Usually the notation is this one. Let's say phi of x1, phi of x0. This is the when you put the annihilation operators on the right, the creation operators on the left. So it's the convention is usually to separate these fields also. Phi of x, remember, phi of x contains the annihilation operators and the creation operators. So we just write that this is phi plus x plus phi minus x. Now phi plus of x is called the positive frequency component. Because it is proportional to this exponent. All the terms in that Fourier series that have that e to the power minus ikx is in phi plus. So this contains the annihilation operators. You see that phi plus is not the dagger of something. Whereas phi minus is the negative frequency component. Negative frequency because in the Fourier representation it contains the plus ikx term or e to the power minus ikx term. The time term in that exponent has the opposite sign. That's why it's called the negative frequency component. And it contains the annihilation creation operators. So if you have, let's say we had the phi x1, phi x0, if you write the normal ordered product, this is phi plus x1 plus phi minus x1 and phi plus x0 phi minus x0. This is equal to phi plus x1, no, not the normal ordered product, phi plus x0. All of them are annihilation operators. Annihilation operators are on the left. Then we have phi minus x1, phi minus x0. Then we have, these are all creation operators. Then we have the phi minus x1, phi plus x0. And then we have phi minus x0, phi plus x1. You see, if you just multiply them, ignore the normal ordering, you would get a phi minus x1, phi plus x0, the product of these two terms. But then you would get phi plus x1 on the left and phi minus x0 on the right. What normal ordering does is, since the annihilation operator in that product is on the left, it switches their order. So it says that first you act with the annihilation operators, then with the creation operator. Inside the time ordering, whether the operators commute or not doesn't really make any difference, because it's the normal ordering itself which determines the order of the operators. Just like in the time ordering itself determines the order with which the operators will be multiplied, so you can just change their places as if they are commuting things. Here the normal ordering does the same thing, but the criteria it uses to order the operator is whether it's an annihilation or a creation operator. Now, how will it affect us? Let's see. We have the phi of x1, phi of x0. This is equal to phi plus x1, phi minus x0, phi plus, this is x1, x0, phi minus x1 under time x0. Well, this will be equal to I have the step function depending on the times, etc. But let me write it in this form. There is something which is normal order. I just change their order. in such a way that eventually everything is will be normal ordered. Plus there will be remaining terms. Now, what is this remaining terms? Essentially, if the operator inside the time ordering is not actually normal ordered, I just replace it with the commutator plus the normal ordered expression. So these remaining terms are just commutators. Okay, so let's see. Let me look at the vacuum matrix element of this time ordered operator. Well, you see, normal ordering has either the annihilation operator on the left or on the right, or annihilation on the right or creation on the left. So they are all zero when I take the matrix element in the vacuum, in empty state. So what remains is just the remaining terms. Which we had already calculated. Let me just give it a name. So what do I have? Time ordered product of phi of x1, phi of x0 is actually phi of x1, phi of x0 plus, well, the notation is usually this one, phi of x1, phi of x0, so-called contracted. This is called a contraction. Let's write it explicitly. I mean, again, it will be something boring, but I mean, we will be using it eventually. Now this, let me just copy this term. So this is, let me just multiply it out, time ordered product of phi plus x1, phi plus x0, plus time ordered product of phi minus x1, phi minus x0. And keep in mind, phi plus containing only annihilation operators, they commute. Similarly, phi plus, since they contain the annihilation operators, they also commute. So it doesn't really matter whether we write the time ordered product or not over there. They will commute. And plus, we have the time ordered product of phi plus x1, phi plus x1, phi minus x0, plus time ordered product of phi minus x1, phi plus x0. Well, let's see. The first two terms are already normal ordered. Then I have, you see, the time ordering, we had already derived it before. Time ordered product of two operators. This was T1 minus T0, T2 of T1 of T2, or 1 minus theta of T1 minus T2 of T2 operator at T1. So this was equal to, no, let me write it, sorry. Let me write the theta of T2 minus T1 over here. And this is 1 minus theta of T2 minus T1. So this is equal to operator product of T1 and T2 minus theta of T2 minus T1 times the commutator of O of T2, O of T1. In fact, maybe it will be shorter to directly use this one. So let me go back. This is what I'm interested in. I know that this is phi of x1, phi of x0, minus theta of x0, 0 minus x1, 0 of phi of x0, phi of x1. Now the first term is phi plus x1, phi plus x0, plus phi minus x1, phi minus x0, plus phi plus x1, phi minus x0, plus phi minus x1, phi plus x0. Minus theta of x0, 0, minus x1, 0, phi of x0, phi of x1. Okay, so let's see, this is already normal ordered. This is already normal ordered. Phi plus, phi minus contains the creation operators. This is not normal ordered. This is already normal ordered. Well, I can use the commutation relation, so I can just write this as, I can add phi minus x0, phi plus x1, and subtract phi minus x0, phi plus x1. So this becomes, okay, the first term, the second term, the fourth term over here, and this term over here. They are nothing but the normal ordered product of phi of x0, phi of x1. What remains is I have the plus commutator of phi dagger of x1 and phi minus of x0. Minus, okay, here we have the step function. Inside the remaining commutators, the existing commutators are, let's see, phi plus of x0, phi minus of x1. This commutator is non-zero. And then we have phi plus of x1, phi minus of x0. No, phi minus of x0, phi plus of x1. Otherwise, I have a sign mistake. Or what do we obtain? Phi of x1, phi of x0, their time ordered product is actually equal to the normal ordered product so I can combine this term and this term. So let me see, theta of x0, 0 minus x1, 0, phi minus of x1, phi plus of x0, I don't have any sign mistakes anywhere. let's see, this is plus, then I have, this is the second term. Oh, okay, no. No, this is the first term. The second term combined just gives me 1 plus theta of x0, 0 minus x1 of 0 of phi plus of x1, phi minus of x0. Now there's a sign mistake somewhere, most probably. Now, let me just have a fast check. So here, if T2 is larger than T1, then we have OT1, OT2. The other way around, I have the 1 minus OT1, T2. So here, I have OT1, T2, the first term. And then I have T2, T1. There is a minus sign over there. If there is a minus sign, so okay, so this is a plus sign, sorry. So the time ordered product phi of x1, phi of x0 is the normal ordered product plus theta of x0, 0 minus x1, 0 of phi plus x0, phi minus x1 plus theta of x1, 0 minus x0, 0 phi plus x1, phi minus x0. Okay. Okay. And the last two lines is actually what we call the propagator. Now, my claim will be this one. Let's do an example with 3 fields. Or 4 fields. No, 3 fields. Now, I already know that inside the time ordering, I can just exchange the position of the operator. It doesn't make any difference. Okay, so what I will assume is that I can easily make that assumption. If this is not satisfied, just change their order. So eventually you will get a form in which this is satisfied. So this is actually equal to phi of x1, phi of x2, phi of x3. I can even just remove the time ordering completely. Well, what do I know? That time ordering over there is actually the normal ordered of phi of x2, phi of x3. And then if you look at this expression over here, the time ordered product of 2 fields, x3, 0 is larger than x2, 0. So I will get the commutator of phi plus, which is the larger one, x3, and phi minus x2. Now this will be equal to, now Now this phi, capital Phi, will be phi plus x1, phi minus x1, normal ordered product, phi of x2, phi of x3, plus phi of x1. But you see, phi of x1 is already, I can consider it to be a normal ordered product. There are no products, so normal ordering doesn't do anything. Of phi plus x3, phi minus x2. Now let me see this phi minus. Remember, it's the creation operators. Normal ordering places the creation operators on the left. But this is already on the left. So the first term is already normal ordered. Then I have the phi plus. Now, you see, this term is not in normal ordered product. To put it in normal ordered product, I have to use commutation relations to move the annihilation operator over here towards the right. So, for example, what kind of terms I will get in this normal ordered product? I have phi plus, this is at x1. Inside the normal ordering, I get, for example, phi minus x2. No, let me not write it explicitly. Let me write it explicitly once. So I have the phi plus. That normal ordered product, okay, let me write everything out. I have the normal ordered product of phi minus x1, phi of x2, phi of x3, plus the normal ordered product of phi of x1, phi dagger of x3, phi plus of x3, sorry, not the dagger, phi minus of x2, plus phi plus multiplying with phi plus of x1 multiplying phi minus x2, phi minus x3, plus phi plus x2, phi plus x3, plus phi minus x2, phi plus x3, plus phi minus x3, phi plus x2. Now I need to take the commutators. Phi minus of x1, phi of x2, phi of x3. These are all in normal order. Now let me look at the first term. If I just commute them, I will eventually obtain this expression. Phi minus of x2, phi minus of x3, phi plus of x1. But then I already have to take into account the commutators of phi plus of x1, phi minus of x2, phi minus of x3, plus phi minus of x2, commutator of phi plus of x1, phi minus of x3. Okay, this is the first term. I just added the commutators. The second term is already in normal order product, so I don't need to do anything about that. You see, the first line over here is in normal ordered product, so I can just put it inside normal ordering. Now this term over here, it contains all annihilation operators, so it's already in normal ordered product. I don't need to do anything with that. Then I have the third term in this parentheses. I have to commute phi plus and phi minus. It will become phi minus of x2, phi plus of x1, phi plus of x3, then plus phi plus of x1, phi minus of x2, phi plus of x3. And finally, the last term, I have to commute phi plus of x1 with phi minus of x3, so it becomes plus phi minus of x3, phi plus of x1, phi plus of x2, plus the commutator of phi plus of x1, phi minus of x3, and now we have phi plus of x2. Okay, so these are already in normal ordered product. This is already in normal ordered product. Now what do we have? Let me just try to combine them. Do I have everything? Yeah. No, I forgot one term. I have the plus phi of x1 times the commutator of phi plus of x3, phi minus of x2. Now let me look at four terms. I have this term, I have this term, and I have this term. Now they all contain phi plus of x1, so let me write them out. So I have the phi minus of x1, phi of x2, phi of x3, plus, well, inside the normal ordering, I don't really need to worry about in which order I write the operators, because it's normal ordering which orders them. So they all contain phi plus of x1. So let me, okay, did I write everything down? Okay, so this first line is from this line, is from this term over here. This line is already over here. The third line, phi minus x2, phi plus x1, phi plus x3, is over here. Oh, and then I have this fourth line, okay. Now I'm combining these four terms. This term, this term, this term, and this term. I'm combining all of them. They all contain phi plus x1. Phi plus x1 over here, phi plus x1 over here, phi plus x1 over here, phi plus x1 over there. What remains is nothing but phi of x2, phi of x3. Well, each one of these phi's contains two terms. If you just multiply them out, you will get four terms with all possible combinations of plus minus at x2 and x3. You see, here you have the minus minus x2, x3. Here you have the plus plus x2, x3, and here you have the minus plus x2, x3, and here you have the plus minus x2, x3. So all possible products. So all those four terms in ellipses just combine to give me this term. Now what remains is, so let me see, this term over here is phi plus x3, phi minus x2. Do I have a similar term? No, let me just write it down so that I will probably see it. Okay, the additional terms I have, which I didn't write yet, this one. What else? I have these two terms. And then I have these two terms. Sorry. So let's see if there are any simplifications here. Here I have phi plus x1, phi minus x2. So similarly over here, these two terms are the same. I get here phi plus of x3, here phi minus x3. So I can just combine them. So it just gives me phi at the position x3. So let me just erase this term. And this just becomes phi at the point x3. Well, the field itself is not a product, so whether you put it in time ordering or normal ordering, it doesn't make any difference. Let me just put it in normal ordering. Now let's look at these two terms, last two lines. They are both phi plus x1 and phi minus x3 commutators. These are just numbers. Since they are numbers, I can commute them. I can just commute this phi plus and move it to the front, to the back, as you wish. It doesn't really make any difference. So I can just combine these two. And it just becomes here phi at x2. And again, since this is just a field, not a product, whether I put it in a normal product or not doesn't make any difference. So what did we have? We started with the time-ordered product of phi of x1, phi of x2, phi of x3. Now this became, well, you see here we have two normal ordered products. Well, just like in the time ordering, the normal ordered product is a linear. That's how we defined it. So I can just combine these terms. Phi x2, phi x3 is the same in both of them. So it's just phi plus x1 and phi minus x1. They are summed. That is phi of x1. So this three operators under time ordering just becomes phi of x1, phi of x2, phi of x3 under normal ordering. Then I have those additional terms. Plus phi of x1 normal ordered, and the commutator of phi plus x3, phi minus x2, plus normal ordering of phi of x2, phi plus of x1, phi minus of x3, and then we had plus normal order of phi of x3, phi plus of x1, phi minus of x2. Okay, this is what we ended up having. Now let's just go back to our starting point. Okay, so this is what we had. We had the time-ordered product of three fields. So what did I do? I just assumed a particular time ordering for the fields, because I don't really lose any generality, because essentially I can just change their position. So here this is x1, 0 is larger than x2, 0 larger than x3, 0, x1, 0 is the latest time. Now, also if we go back over here, if x1 is later than x0, let's say, then we have the phi dagger, phi plus of the later time, and the phi minus of the earlier time. Okay, that is also something to keep in mind. So I have the time ordering product of these things. x2 is larger than x3. Sorry, I have a side mistake over here, right? So here, this definition is not phi plus of x. Okay, so let's go back. Here I have the time ordering, the definition. If x1 is later than x0, I have the phi plus of the later time and the commutator of phi plus of the later time and phi minus of the earlier time. That is the time ordered product of two things. So here the later time is x1. And this is x3. No, x2 and x3, sorry. So let me just make that correction all the way down. This is x2, this is x3. Okay. So, and then, okay, I just assumed a particular ordering. Then for that case, I just took one of them out of the time ordering. What remained is just two operators in the time ordering. I can write that time ordering product as the normal ordered product plus that commutator because it's just the two fields. And then what I did was we just wrote it explicitly out. And if any operator was not in normal ordered product, I just used the commutators to put them in normal ordered product eventually. And this is what I obtained. And also keep in mind that our conventions was that all of this thing we denoted as the contraction of phi of x1, phi of x0. That is the notation we use. And that notation basically tells us that take the positive component of the later time and the negative component of the earlier time, take their commutator. And remember, x1 is larger than x2. x1 is the latest, x3 is the earliest. So this time-ordered product, phi of x1, phi of x2, phi of x3, is actually this normal ordered product, x1, phi of x3, plus the normal ordered product of phi of x1. Let me just write it this way. You see, look at this one. x2 is the later time. Positive component of the later time and the negative component of the earlier time, we are taking the commutator, but that is what we defined as the contraction. Well, the contraction itself is just an ordinary function of the positions. It's not an operator. So whether we put it in the normal ordering or out of the normal ordering doesn't really make any difference. So that's why I prefer to put it inside the normal ordering, just for notational convenience. And let's look at the second term. The positive component of the later time, which is x1, and the negative component of the earlier time, which is x3, I take their commutator. This is the definition of the contraction. No, sorry, x1 and x3. No, this is plus the third term. This is x1 is the later time, the positive component of the later time. x2 is the earlier time, the negative component of the earlier time. Take their commutator. Again, this is the definition of the contraction. So what happened in the case of three fields? Well, the time-ordered product of three fields is actually the normal ordered product of those three fields plus all possible contractions. There are three different ways you can just contract the two of the three fields. So you have all possible contractions over there. Now, you see, look at this one. Just let's look at this one. This is equal to of course, you have to keep in mind the order of the things that you do. Commutator you evaluate first. But that commutator is just an ordinary function. It's not an operator. So operator, since it's just an ordinary function, just put it wherever you want. Before the operator, after the operator, because it's just a function. But of course, if you first write down the normal ordering and then try to calculate the commutator, you would be doing a mistake. Because the normal ordering already determines the order. The commutator, formally inside the normal ordered product, the commutator is just 0. Because it's the normal ordering which determines the order of the operators. But here we should understand that first you calculate the commutator and then the normal ordering. With that understanding, these two terms are equal. Essentially because it's easier to understand, to remember. I mean, so this is the one example of what we call the Wick's theorem. Which basically states that if you have the time-ordered product of an arbitrary number of operators, this is always equal to the normal ordered product plus all possible contractions. You see, if you go back, what happened over here? The contractions, what we call contractions, are just commutators. So we started from here. Any term that's not in normal ordered product, we try to put them in normal ordered product by just commuting them. But those commutators just resulted in contractions. what we call contraction. So the proof is also by induction of the theorem. So you just assume that okay, the proof by induction basically, I mean, in one of your homework, I mean, you try to do an induction, but you kind of seem to have missed one step. What you do in induction is you assume that the claim is true. Is true for the product of n-1 operators. And then prove for n operators. Again, that's actually what we had done in the case of 3 operators over here. You see, we started with 3 operators. Without loss of generality, I can just assume their time to be ordered in any particular fashion. If they are not ordered in that fashion, I can just change their ordering and put them in that order. And then if that is the case, I can take the latest operator out of the time ordering on the left. And then what remains is one less product of one less operators. For this one, I can use the Wick's theorem. I can use my assumption. Here I did it. This is the time-ordered product of 2 operators is the normal order plus their contraction. That is what I assumed. And then what I did was here this phi plus, the phi minus component is already in normal ordering. I can put it over there. But then I have to commute phi plus all the way to the other side. But then I get all the commutations of phi plus at x1 with phi minus at the other space-time points. But those commutators are what we call the contractions. They're just numbers. And hence you have the proof. Let's see a concrete example. Let's see. Let's look at this one. Let's even look at the okay, let's first an example in operator form. Phi of x1, phi of x2, phi of x3, phi of x4. What Wick theorem tells us is that this is equal to this normal ordered product plus all possible contractions. Now, what does it mean, all possible contractions? I can have one contraction I can contract x1 and x2, or I can contract x1 and x3, or I can contract 1 and 4. Okay, there will be many terms. I can contract 2 and 3. Or 2 and 4. Or 3 and 4. These are all possible single contractions. But then I have 2 contractions. I can contract 2 pairs. I can contract phi 1 and phi 4, and then what remains is phi 2 and phi 3. Or I can contract phi 1 and phi 3, then phi 2 and phi 2 will be contracted. Or I can contract phi1 and phi2, then phi3 and phi4 will be contracted. So this is the Wick theorem. So it says that if I have considered the product of four operators, then I can write it as how many terms? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms, the sum of 10 terms. Well, most of the time we don't really care about the time-ordered product itself. We want its matrix element between the empty states. When we have the empty states, if there are any operators left, they will just give me 0. So this is simpler. Well, you see, what does this tell me? This tells me that take phi of x1 and phi of x2, take their positive, negative parts, and replace phi of x1, phi of x2 with their commutator, the commutators of positive and negative frequency parts. That commutator is just a number. But in that normal ordering, there is still phi of x3 and phi of x4. Those are operators. And what normal ordering does is it makes sure that there is an annihilation operator on the right and a creation operator on the left. But if you take the vacuum matrix element, it just gives 0. Either the annihilation operator acts on the ket and annihilates it, or the creation operator acts on the bra and annihilates it. So the only terms that remain in this time ordering product is when this matrix element is when all the fields are contracted with some other field. And those are just the last 3 terms, these 3. So this is equal to phi of x1, phi of x2, phi of x3, phi of x4. And you have the contraction of 1 of 4 and 2 and 3, phi of x1, phi of x2, phi of x3, phi of x4. And you have the contraction of 1 and 3, and 2 and 4, and plus phi of x1, phi of x2, phi of x3, phi of x4, and then you have the contraction 1 and 4, and 2 and 3, and 1 and 2, and 2 and 3. Well, usually we don't just write these formulas. We usually just show it by graphs. What do you mean by graphs? We essentially have 4 points, x1, x2, x3, x4. x1, let's say x2, x3, x4. x1, x2, x3, x4. x1, x2, x3, x4. And remember, these contractions are essentially what we call propagators. It gives us the amplitude for the particle to go from one point to the other point. Well, let's see. In the first term, is x1 goes to x4, and x2 goes to x3. The second term, x1 goes to x3, and x2 goes to x4. The third line, x1 goes to x2, and x3 goes to x4. So these are the 3 Feynman diagrams that contribute to our initial amplitude, initial 4-point function. Well, you see, there are a couple of issues. Here we are considering a real particle, a real field. If you remember when we were looking at the first computation, at the point where we started, to make sure, to explicitly show that which particle goes from where, which point to which point, I said that let's put phi plus phi dagger at x0 and phi at x1. So here it was at least superficially clear which particle was created first, and then it went where. So it was created at x0. But for a real field, well, phi dagger and phi are the same thing, because the field doesn't actually only create it. It has both the creation and the annihilation. Now the time ordering, let's look at the time ordering. What does it tell us? We looked at such an operator. Later on, I just dropped the assumption, I just dropped the dagger, since it was a real field. And I dropped any assumption on which time is first and which one is the next one. You see, what is this one? This is equal to if x10 is larger than x00, then this is phi of x1, phi of x0. If it is the other way around, this is phi of x1, x0, phi of x1. Well, this is what's called the Feynman propagator. You see, if x1 is later than x0, then you create a particle at x0. You see, here phi contains both the annihilation and creation operator, but the annihilation operator doesn't do anything. It annihilates, it doesn't contribute, it's the creation operator. So if x1 is later than x0, you have a particle creation at x0, and then it propagates into x1. If it is the other way around, you have a particle created at x1, which propagates to x0. So you first create the particle at whichever space-time point is early, which propagates afterwards, which you measure afterwards, later on. You see, currently, if we are not specifying, but okay, so let me put it this way. We have two options. Either we can say which one, x1 or x0, which one is early. Either we can specify it, say that, okay, at t0 I create a particle, and I look at whether it goes to x1 at a later time. So then I'm explicitly specifying it. In that case, only one of these terms contribute. Or the other option is you don't specify it. It will be relevant in a moment. Even if you specify it, let's say that you create a particle at x0. You say that x0 is earlier than x1. Then there's no time ordering anyway. There's no using of there's not. Okay, let me come to that later on. Because later on, what will happen is, let's calculate the correction to single particle propagator. Okay. Yes, we were looking at this one. So in this term, everything was clear. x0 was early, x1 was later on. And we said that, okay, this is the same thing as time-ordered product, phi of x1, phi of x0, and then we have the e to power minus I dt v of t from minus infinity to infinity. So this is what we have. And as a concreteness, I will assume that v of t is actually lambda over 4 d cubed x, lambda over 4 phi to the 4, or dt v of t is actually d4x, the 4 over 4 space-time over space-time divided by 4 factorial phi to the 4 of x. Okay. Now we said that how do we calculate this? Phi of x1, phi of x0, e to power minus I from minus infinity to infinity dt v of d4x d4x lambda over 4 phi to the 4 of x. Let's just look at the numerator first. This is equal to time ordered product of phi of x1, phi of x0. The first term in the exponent. I'm just expanding the exponent. Then I have minus I d4x lambda over 4, 0, time ordered product of phi of x1, phi of x, phi of x0, phi to the 4 of x. Then I have the second term, minus I lambda over 4, d4x1, d4x2, this is squared. There is I have 4 factorial. There is 1 over 2 because it's the second term in the exponent, d4x1, d4x2, time ordered product of phi of x1, phi of x0, phi to the 4 of x1, phi to the 4 of x2, I have infinitely many terms. Let's look at them. First, I have this one. This is just, here I have x0, here I have x1. I only have the propagator. So here in this term it's clear, x0 is early because I told you that x0 is early, x1 is later, so it's just the propagator from x0 to x1. Then I have the second term. Minus I lambda over 4 phi to the 4 of x. Let's look at the diagrams. You see there is one point x0. There is another point x1. Now, let me go to the next page. There is one point x0. There is one point x1. And there is a point x. But I have 4 fields at the point x, not just one field. So just to denote the 4 fields, let me just put 4 lines. Now, possible contractions will be just pairing the fields. And in fact, in x0, let me put a line, and x1, let me put a line. Each one of those lines actually correspond to a field. And Wick's theorem tells me that I should consider all possible contractions. Well, contraction is nothing but how do you pair your fields. So I should consider all possible pairings of these lines. Now, what are they? Well, one case will be x0 to x1 straight away. Then I can pair these ones among themselves. But keep in mind, here I have 4 lines. This line I can actually pair with 3 of the other fields. I have 3 cases. So I should multiply this term by 3. That is one thing that I should keep in mind. And if you would like to write down the corresponding expression here, you see this contraction gives me, we call that x1 minus x0. Here I have 2 contractions, one contraction x with x, and another contraction x with x. And then I have this additional factor of minus I lambda over 4. So this diagram contributes to such a contribution, lambda over 4 factorial. Now what are some other possible contractions I have? I have x0, x1. Well, instead of contracting x0 with x1, I can contract x0 with one of the fields leaving x. How many different fields I can choose? 4 of them. And then x1 I can contract with, there are 3 fields remaining at the point x. I can contract x1 with any one of them. So there are 3 different ways, 3 different identical contributions. So that's why there is 3. And then I have 2 fields left because at the point x I have 2 fields. So x and x. Now what is the corresponding contribution from here? Well, there is a minus I lambda over 4 factorial. It is this term, this coefficient over there. Then I have x s, okay, x goes to x0, x1, no, x0 goes to x goes to x1, and then x goes to x. This is another propagator, another contribution. And of course, I need to multiply it with 4 and 4 times 3. And any other possible geometries? Not really. These are all possible cases. Now let's go to the other case. Of the order of lambda square. So what do I have? This is the lambda square term over here. I have 4 fields at the point x1, 4 fields at the point x2, and 1 field at x0, 1 field at x1. Oh, sorry. Let me just change my notation slightly. Let me call these y1 and y2. So that y1 and x1 will not change. You see, this x1 over here is the x1 that appears over here. This y1 is my integration variable. So of the order of lambda squared, I have the point x0, I have the point x1, I have the point y1, I have the point y2. Now what are the possible geometries I can write down? Okay, let me just, there will be many cases over here. One thing is x0 can just straight away go to x1. And then we have y1 and y2. This is just one possible geometry. x0 goes straight to x1, and these y1 and y2 fields, they are each contracted among themselves, not between themselves. Or I can also have contractions between themselves. Now what happened over here? x0 went to x1. 2 of the fields at y1 are contracted with 2 of the fields at y2. And the remaining 2 fields at y1 are contracted among themselves. Remaining fields in y2, they are contracted among themselves. Or I have this possible case. x0 goes to x1. Each field at y1 is contracted with a corresponding field in y2. There are these cases. x0 is contracted with y1, which goes to x1. And the remaining fields at y1 are contracted among themselves. y2 fields at y2, they are contracted among themselves. This is one field, one contribution. Well, you see, for each such diagram, use x0 instead of y1, you could have just chosen y2. and it will give exactly the same result. You are just changing y1 and y2. So those diagrams, I can just multiply them by 2. The other factor corresponds to x0 going into y2 and y2 going into x1, and y1 being separate somewhere else. And what else I have? X0 goes into y1, which goes into x1. So 2 of the fields at y1, they are already contracted. The remaining 2 fields at y1, they are contracted with y2. And what happens in y2 is there are 2 fields remaining in y2, so they are contracted among themselves. X0 is contracted with y1. One of the fields is already contracted. There are 3 fields left. Those 3 fields can be contracted with y2. So there is 1 field left at y2 which is contracted with x1.
Also, in the second case from the last line, that's also like we would multiply.
Sure. Now, in fact, we need to multiply even by more terms, more factors. Let's calculate the factors. Let's start with the first term. Let me just separate them so they don't get confusing. You see, x0 is contracted with x1. There is a single way of doing that. At y1, just pick up any field. It can be contracted with 3 of the remaining fields, so there's a factor 3 there. Similarly for y2, each one of the fields in y2 can be contracted with any one of the 3 remaining fields. And once you determine with which field it contracts, so 2 of the fields are already contracted, you only have 2 fields left. They have to be contracted by themselves to create diagrams like that. Now let's look at this one. Okay, x0 goes to x1 in one single way. Now, among the 4 fields in y1, we have to choose 2 of them. In how many different combinations you can choose? 6 ways. In y2, you can also choose 6 different combinations. So it's 6 multiplied by 6, so you already have chosen 2 fields in y1, 2 fields in y2. You can contract these in 2 different ways. 6 times 6 times 2. Let's look at the third one. You pick up the first field in y1. It can contract with 4 different fields in y2. So that brings 4 different contributions. So at each point, 3 fields are left. You can take the second one in y1, which can be contracted with 3 different fields on the y2. So you get 4 factorial combinations over there. Let's continue. Okay, we said there is a factor 2 because you can just exchange y1 and y2. And in y1, there are 4 fields. x0 can be contracted with any 4 of them. So there is a factor 4. And so in y1, there are 3 fields left. Any one of them can be contracted with the field at x1. There are 3 possibilities. So 4, 3, 2. Here, you see, here there are also some possibilities. You pick one. The first one can be contracted with 3 of the remaining fields. This is due to y2, that 3. Now let's look at over here. We have a factor 2 because y1 and y2 can be exchanged. Now x0 can be contracted with any 4 of the fields at y1. There are 3 fields left. x1 can be contracted with any one of those fields at y1. There are 3 left. So there are 2 fields at y1. Now in y2, we should pick 2 fields in y2. We can pick that in 6 different ways. So we pick the two fields that the two fields at y1 will be contracted, and there are two possible ways of contracting them. And the field at y2, two fields left, there are no possible contractions left. Let's come over here. This 2 is because we can just exchange y1 and y2. And then we have x0 can contract with any 4 of the fields in y1. x1 can be contracted with any 4 of the fields in y2. So at y1 we have 3 fields left. Pick any one of them. It can be contracted with 3 fields at y2. 3 times 2 times 1. So these are the factors corresponding to each diagram. And if you pick up any diagram, let's just pick up this diagram. We can in fact write down the corresponding contribution right away. Because each contraction is actually a propagator. So this is, we have a propagator from x0 to y1, a propagator from y1 to x1, and two propagators from y1, y2 to y1, and one propagator from y2 to y2. Well, what space-time point is y1? We don't know. It can be any space-time point. So we integrate over y1, and we integrate over y2. Now, for each what we call vertex, those are what we call vertices. They are just each v terms in our expansion. But you see, each v term comes with each potential term comes with a factor minus I lambda over 4 factorial. So here we have minus I lambda over 4 factorial squared, because we have two vertices, not just one. Each vertex brings a factor minus I lambda over 4 factorial. Then this is the second order term. So there is from the exponent we have a 1 over 2 factorial. But you see, this 2 is already cancelled by this 2 over here, because we can change y1 and y2. So usually when you look at what are called the Feynman diagrams, you just ignore these 2. And also ignore the 2 factorial from the exponent. Because if you go to the third order term, from the exponent you will get 1 over 3 factorial, but then you will get 3 points y1, y2, and y3. You can just pick up any one ordering of y1, y2, and y3. There are 3 factorial possible orderings, but all of them will contribute the same. So those orderings will again cancel that 1 over 2 factorial or 1 over 3 factorial. Now what is left? Then we have this here 4, 3, and 2, 4 factorial. And then 6 is 3 times 2, that is 4 factorial divided by 2. That is 6. No? Yes. No. No, 6 is 3 times divided by 4, sorry. Now let's see. You see, this factor from the exponent is cancelled by this 2. And if you look at the nth order term, at least in these connected diagrams, let's say, you will get 1 over n factorial from the exponent, but when you are calculating the contributions of the diagrams, you will get also n factorial from there. So they will always cancel. Here you have 1 over 4 factorial squared. You see, 1 over 4 factorial squares, they also always cancel. So whenever you look up the Feynman diagrams, Feynman rules, let's say, the Feynman rules is that for each vertex, you assign a factor minus I lambda. For each propagator, you write the corresponding expression, and then divide by the symmetry factor. Well, you see, in this case, the symmetry factor is 1/4. You see, if you exchange these two lines over this one and this one, nothing changes. That's the symmetry of this diagram. You just flip them. Well, similarly, if you have this bubble, you just flip them, rotate them. Still the same diagram. So 2 times 2, you have 4-fold symmetry. So that's the symmetry factor. You see, I always have difficulty calculating those symmetry factors. So that's why I always count the contributions. That I find easier.
How come the changing this bubble can contribute anything if it's just one propagating it?
Well, you just flip it. You see, it doesn't change. That's the idea of the symmetry. It doesn't change anything.
Basically, I don't understand. I don't see if there is anything to flip on that thing.
Exactly. The point. Nothing is.
The other ones were like 2 propagators that you could just switch, but this one is just only one. Like, how could you?
You see, they are connected by a point. You see, even that doesn't really give a new diagram.
If they are like regular normal space points, we can just put axes and switch axes
Yeah.
on that and flip like that.
You see, as I told you, I always find it difficult to calculate so-called the symmetry factors. So I always go along this path. If I find it easier to just count how many diagrams I have and insert the factors. The nice thing about, for example, the standard model is you don't get them. The symmetry factors are always 1. Because the fermions, when we study the fermions, we will see that they are not just lines, they are direct, so-called the directed lines. You put arrows there. So I will not be allowed to flip the loop, for example. There will be arrows pointing there. So I don't get the symmetry factor. And okay, let's continue. Okay, it's already. Let me just mention one more thing. Okay, the symmetry factor, as I told, I also find them confusing. So I just count the factors. Any questions on how to draw the diagrams? It's just connecting lines. Just connect them so that there are no free lines except then the ones that you determined from the beginning that should be free lines. And then each line contributes a propagator, just like this one. And each vertex contributes a factor minus, depending on how you will be counting the factors, either minus I lambda or minus I lambda over 4 factorial, depending on, as I said, how you like them. And the difficult thing will be just determining the overall factor. There are the factors from the exponent, the factor from the exchanges of y1, y2, etc., and the possible different contractions which I actually give exactly the same result. Now, you see, up to this point, what we had considered is, okay, we were looking at the two-particle propagator. And that two-particle propagator had 2 parts, the numerator and the denominator. We only looked at the numerator. We didn't look at the denominator. And we had seen that the numerator, it has many terms, but it also has such terms. This one with an external point. This one with external 2 points. That one with external 3 points. External 4 points, external 5 points, etc. But this is actually this one. this fact, if you write the Feynman rules, Feynman diagram, the corresponding contributions, what you will get is just the 2.3 propagator multiplied with 1 plus this one plus that one squared plus that one cubed all the way out. Now, if you would write the other diagrams, for example, along with this one, you will also get such a diagram. Then you will get two of them. Then you will get three of them. You get all those terms. Now let's look at this, the numerator. You see, we have the denominator and we have the numerator. In the numerator, we don't have any. Let me just write the numerator. If you expand the exponential, you will get 1 plus a single v, which is just 4 fields at the same point. You get terms with, in the square term, you get terms with 2 v's, which will have contributions of this form. And then you will have 3 terms with 3 v's, from which you will obtain contributions like this. But that is actually just this parentheses. Of course, the factors could have been different. You see, all these diagrams, they will come with various factors. And the factors also turn out to be the same. So all these diagrams are actually nothing but the denominator. And similarly, if you have, for example, there is such a diagram. In our expansion of the numerator, which will also, if you calculate higher order terms, you also get all these. If you sum them up, you get this contribution multiplied with 1 plus this one plus that one squared plus all the remaining terms. Of course, you have to pay attention to the factors. So actually, this is what we call a connected diagram. There are no separate pieces. For example, this is a disconnected diagram. It is made up of 2 separate pieces. In the expansion of the numerator, you will get every connected diagram will be multiplied by all these terms. Well, what are those terms? They are just, you have the V, the fields in V in the exponent contracted among themselves. But the numerator is exactly the same thing. You have the fields coming from V contracted among themselves. They essentially cancel each other. So what we have actually shown vaguely, as you might guess, it will be your homework to check at least a few of the factors that they actually match. You see, we started by looking at this diagram, this term. And we had shown that this is actually the vacuum empty, the zero matrix element of the time ordered product of phi of x1, phi of x0, e to power minus I v of t dt from minus infinity to infinity divided by the numerator. But the numerator just basically cancels all these disconnected pieces. So when you are calculating the numerator, if you only take into account the connected diagrams, we are done. There is no numerator left. Now, okay, any questions up to here? I will ask you to actually check some of the factors. So probably there it will be easier for you when you see on your own that it actually works. Okay, so just one point before you go. You were asking about where do these particles propagate from? Where do they go from? From x0, x1, or where? Let's look at this diagram. There is this contribution. And we said that, okay, this diagram we can write as Sx minus x0, Sx1 minus x, and Sx minus x. We have the d4x and minus I lambda over 4 factorial. Then we have the 4 times 3 factor. That's it. You see here the symmetry factor is actually 2 because that you see that bubble. You can just flip it, the same thing. So what are the possibilities? You see, we are integrating over all d4x, all space-time points. So if you want to imagine that chronological order, we already know that x1 is later than x0. Okay, that chronological order we already know, but we don't know when is x. For example, it is possible that before x0, you see, possible chronological orders. You see, let's take this as time. That is one possible chronological order. x0, x1. So what do you know? You know that at t0, x0 there is a particle, and you are looking at if there is a particle at t1, x1. Okay, so that is what you are asking for. So here in this diagram, what happens is you have a particle at x0, which goes to the point x, and since it's at the point x, if you like, you can imagine it as splitting into 3. And one of them just goes to x1, and the other 2 they just they just stay there. They just stay there. Or let's say at x1, it starts at x1 and ends at x1. Another chronological order would be this one. So x is even before x0. So what the particle at x actually came from x0. No, the particle at x0 at the time t0 actually came from x0 in this chronological order. And then at the time x there was another particle which just went to x1. So what you know is at t0 there is a particle at x0, at t1 there is a particle x1. And there is this other particle which started at x and ended at x at the same time. It just is created and at the same time destroyed at the same point. Another chronological ordering is this one. So the first there was a particle at x0, which went to the point x at the time t. Then at x1, okay, this I don't know how to interpret without using time travel. You see, a couple of problems with this example is that we are using real fields. I mean, I want to avoid time travel and I want to avoid antiparticles for the time being. So this chronological ordering will be somewhat problematic. So what this tells me, there is a particle at x0, there is a particle at x1. Well, yeah, that makes sense. There is a particle at x0 and there is a particle at x1. That is what we observe, right? Then the particle at x0 goes to x, the particle at x1 goes to x. And there they just they are converted to a third particle which is destroyed as the moment it is created. Now the Feynman propagator basically takes into account all these possible chronological orders. The particle propagates from the earlier time to the later time in all these cases. Now later on when we start discussing antiparticles, we will say that a particle propagating forward in time will be exactly the same thing as an antiparticle propagating backward in time. But that will be essentially a mathematical trick, let's say. The idea here is what you observe. What you observe is a particle at the time t0 at x0 and the particle at t1 at x1. You are asking for that probability. You don't know whether the particle is destroyed at x1 or what it does afterwards. You don't really know. It can go to the point x.
Once we know that x0 is earlier than x1, we can't swap these two propagators, right? It does not happen symmetrically.
What was Sx minus y? It was plus or minus? It was minus. Divided by k squared minus m squared plus I epsilon with a minus I. This was the Feynman propagator. So let me change k to minus k in all of them, everywhere. But this is the same thing as they are the same. Because you see, essentially this propagator is nothing but the if x0 is earlier than y0, it is the amplitude for a particle to go from x0 to y0. If it is the if y0 is early, it's the amplitude for the particle to go from y0 to x0. Both are in this description. Now later on, as I said, when we are dealing with antiparticles, when you change the order of the time, you will also be changing the particle and antiparticle. Either if you have these two space-time points, it will be either particle moving in that direction or antiparticle moving in the opposite direction. You see, for example, in this diagram, you can interpret this in that case, we will be interpreting it in various ways. One way is at some point, space-time point x, 3 particles are created. One of them is just destroyed the moment it is created. That is this loop. One of them goes to x0, one of them goes to x1. That is one interpretation. Another interpretation of the same chronological order is the particle at x0 goes backwards in time to the point x, where it is converted into 2 particles, one of which is immediately destroyed, this loop, and the other one goes forward in time to the point x1. Mathematically, they will all correspond to the same contribution. When we do have antiparticles, this will no longer be true, by the way. Anyway, we will see them later on. Now, any last questions? Now, fermions, I'm trying to avoid them as long as possible for the time being. Well, you see, I would suggest you, and that is what I actually do, is stick with these, with this expansion of the exponential and just counting how many different ways you can consider the contractions. I constantly make mistakes in calculating the symmetry factors. So to be sure, for a given diagram, I just look at the corresponding term in the exponent, and then I just think of what are the contractions I should consider and how many different contractions I can have, and calculate the symmetry factor. The reason why I'm trying to avoid the fermions as much as possible is I would rather first go over the field theory. What is field theory for the simplest case? What we'll be doing, we will be mainly doing the perturbation theory. And how do we calculate the perturbation theory? There is also this was one of the formalisms of the perturbation theory. Another formalism, I mean, you see, will be the path integral formalism. We will also discuss what is the path integral formalism. It has its advantages under certain cases, especially in gauge fields. It's easier to quantize the gauge fields using path integral. And once we build up our formalism, and then we will consider what are the other possible types of particles, like the fermions or the vector bosons, the gauge fields, etc. But then we will have all the necessary machinery to do actual computations with those different types of particles. Sure. Hı hı.
Şimdi en nihayetinde ben bunları hem phys5'le hem arasına koyduğum zaman tek başına kalan fiyatlardan katkı gelmemesi gerekiyor.
True.
Dolayısıyla o zaman mesela benim üç parçacıklı bir üç field'ın olduğu bir interaction yazdığım zaman bu anlamsız bir şey mi oluyor?
vakum matris elemanına bakıyorsan anlamsız değil, sıfır.
Sıfır. Yani bu böyle bir şey, böyle bir interaction olmuyor demek.
Şimdi,
Bunun olasılığı sıfır demek.
şimdi şöyle, interaction'dan demeden özellikle kaçıyorum. Interaction çünkü vakum matris elemanı demek değil. Şundan dolayı mesela ben bu teori, şöyle bir teori de yazabilirim. Mesela şu ana kadar buna baktık. Ben buna bir de şunu ekleyeyim. Ya da let me call it F. Phi cube. I can add this term. Now, if you ask me what this is, this is of course 0. But it doesn't mean that that F term doesn't contribute to anything. If you would like to calculate phi of x1, phi of x2, if you want to calculate this one, so this will have contributions like this. We have this term, the free propagator, so-called. We have, we should only consider the connected diagrams. We have the lambda term. So this will be proportional to lambda squared. Lambda squared f to the 0. And then we will have this term. This will be proportional to f squared lambda to the 0. Here there is an f, here there is an f. At the interaction vertices corresponding to f, I have three fields. So f does contribute, it doesn't mean that it doesn't exist. It's only if you consider the three field vacuum empty state matrix elements, it will be 0. So that doesn't really mean much. When you look at higher orders, you still get the contributions from the three particle vertex. This is called a three particle vertex. This is a four particle vertex. Plus, of course, there are infinitely many terms. You see, even if a process is not allowed kinematically, it might still have a non-zero matrix element. Okay, so let's end here. Unless I cancel it later on, we will have a lecture also on Saturday at the same time.